Nikhil, do you mind if I record the session?
That should be all right.
Okay. So just to let everyone knows, we are started recording this session right now. And welcome to another SIGIR Virtual Forum Learn and Learn series on quantum NLP. We're happy to have Nikhil Khatri here today from Quantinum. Sorry if I pronounced it wrongly, correct me. And then in this series, our goal is to bring people from industry, from academia, practitioners, all closer together on with more hands-on experience on more advanced technology. And in this session will be relatively long. It would be around 90 minutes. So feel free to ask your question. We don't expect you to keep your question until the end. And Nikhil is going to give us some introduction on quantum NLP, and also he will share more Google collabs, and the session is pretty hands-on. So feel free to ask your question, and I'll give the floor to Nikhil. Thank you so much.
Cool. Okay, thanks a lot. So yeah, I'm Nikhil. I work in the Quantum NLP group at Quantinuum, and I'm going to be talking about the lambeq software package that we develop and the field of quantum NLP in general. So before I get started, this is the broad strokes of what I'm going to be talking about. Since I imagine quantum computing is not super familiar to everyone in the audience, I'm going to be giving a brief introduction to what quantum computing is, what quantum computing programs look like. I'll do this in code as well, using lambeq to walk through some basic concepts. Then a brief look at what NLP is, and then move over to what compositional variants of NLP are used to develop quantum NLP applications. Again, I'll demonstrate a lot of this through code in lambeq. And at the end, I'll tie together all of this into an end-to-end example of a QNLP model trained in lambeq. So at any point, if you have questions, feel free to interrupt me, particularly when I'm sharing code and when I'm doing sort of practical bits. I'm very happy to sort of live code and explain things if they aren't clear. So yeah, with that, let's get started. So I work in the QNLP group at Quantinuum. We're based in Oxford, but there's a bunch of different research directions within the QNLP group. So a lot of the work is on compositional intelligence and quantum natural language processing algorithms. So that's developing compositional models of language and developing quantum algorithms, that is, algorithms that can run on quantum computers for NLP applications. In addition to the QNLP and compositional intelligence style of research, there's also a strong line of research in diagrammatic methods for quantum computing, like calculi for optimizing quantum circuits and other operations in the realm of quantum computing, though not all related to QNLP. So within the broader QNLP group, the lambeq software package is developed by Dimitri, Ian, Neil, and myself. And I'm going to be talking to you more about lambeq as I continue through the presentation. So before I dive into practical bits, a brief note on motivation. So quantum computing is a field of very active research presently, and there have been algorithms proposed for quantum computers since the 90s. And there have been algorithms proposed which have asymptotically faster runtimes for widely applied problems, widely applicable problems, asymptotically faster than equivalent classical algorithms. So I think the classic example of this is Shor's algorithm for factoring, which is important for cryptography. There are algorithms for search and for simulation of physical systems, which have similar properties, and where we expect quantum computers to yield advantage in the future. In addition to this long-term expected advantage from quantum computers, there's also been a lot of contemporary research on variational quantum algorithms. in a bunch of fields. So the variational nature of these algorithms implies that there are trainable quantum circuits. So there are trainable algorithms which can be run on quantum devices. So in this setting, it's interesting for us to ask, can NLP applications benefit from quantum computers? Are there NLP applications which can be efficiently and effectively run on quantum devices? And if so, what are the circuits and algorithms that could implement this? So the work that we do on lambeq and the goal of the lambeq software package in general is to aid in these research directions. So with that, let me go into a brief introduction to quantum computing. So in classical computing, the fundamental unit of information is a bit. So it's a single Boolean value, which can be either 0 or 1. It can take just one of two states. Analogously, in quantum computing, the fundamental unit of information is called a qubit. So while a classical bit is just a single Boolean value, a qubit is decidedly more expressive and is represented by a two-element complex vector. So there are two basis states, 0 and 1, as in the classical case, which are represented by these two vectors on screen. Though these are not the only two states in which a qubit can exist. A qubit can exist in any normalized linear combination of these two basis states. So and specifically any complex combination. So the coefficients here, alpha and beta, can be complex numbers. And the constraint is that these are normalized. So the norm of the qubit state vector is still 1. So to represent qubit and to reason about operations on a single qubit, the block sphere is a useful graphical tool. And all single qubit pure states are represented by vectors which lie on the surface of this block sphere. So the two states which we've encountered so far, the 0 basis state and the 1 basis state, form the poles of the block sphere, with the 0 state on top and the 1 state at the bottom. And now we'll see how we can actually manipulate these states and explore the space of states further. Another diagrammatic notation that isn't the block sphere is this sort of circuital notation, where so on the left, the notation around the 0 is called a ket. So that's a ket 0 and a ket 1, which are represented diagrammatically in this setting, where a while carries the state of a qubit and the triangle sets the state of the qubit. So the first while is set to be ket 0, or is set to be the basis state 0. And so the first sort of most intuitive operation which we can perform with on a single qubit is logical negation. So in the classical setting, logical negation is just a bit flip operation where you send bit 0 to bit 1 and bit 1 to bit 0. Similarly, a quantum logical negation operation sends ket 0 to ket 1 and ket 1 to ket 0. In the quantum setting, this is called a poly-X gate. So it sends qubits that are at the top of the block sphere to the bottom and vice versa. And it's called a poly-X gate because it is effectively a 180-degree rotation of the state vector about the x-axis shown on the block sphere. Yeah. So I think at this point I can sort of poll the audience for if there are questions or if something isn't super clear. Okay, I see some thumbs up. Cool. I will continue and feel free to stop me otherwise. So like the poly-X, so the poly-X was a rotation of 180 degrees about the x-axis. And this was with the original basis of 0 and 1. But 0 and 1 is not the only basis in which we can, sorry, I see a hand up.
Yes, I just wanted to qualify these gates. You said that actual state could be any complex combination, normalized complex combination of the two. I don't know what to call them. do these gates then operate, how do these operate on that kind of qubit? So
Right.
it's just it's a rotation in whatever.
Yeah, so the poly X gate is a 180-degree rotation about the x-axis, no matter what the original state of the qubit was.
Okay, I see. Yeah, I got it. Yeah.
And in general, because the 0 and 1 vectors sort of span the state of span the space of single qubit states, it suffices to describe the operation of a gate on just these two basis states, and its action and the gate's action on any other state falls out as a linear combination of its action on the two basis states. Right. So a slightly less trivial gate is the Hadamard gate. So we started with the 0 and 1 basis state, but we could pick any two polar opposite points on the Bloch sphere as a possible choice of basis. So the Hadamard gate changes basis from the 0, 1 basis to the plus minus basis. So it moves the 0 state to the plus and the 1 to the minus. This isn't super important conceptually to grasp right now, but we might use it later in a notebook, and I can explain it further if I use it in a sort of situation where you don't understand. So the poly X rotated about the x-axis. Analogously, you have rotation about any other axis. So the poly Z rotates by 180 degrees about the z-axis, which acts as logical negation on this new basis, which we introduced, plus and minus, where it interchanges plus and minus basis states. And in general, we had a 180-degree rotation, but you could pick any angle theta by which to rotate state vectors about an axis. So an Rx theta gate can rotate a vector by an angle theta about the x-axis, and Rz theta by any arbitrary angle theta about the z-axis. And in general, you can express any operation on a single qubit by just multiple layers of x and z rotations with different angles. So far, we've only been acting on a single qubit. But a single qubit case is not super interesting because we're dealing with very small data. It's only a 2-element vector. And a lot of the interesting properties of quantum algorithms and quantum devices in general only emerge in the multi-qubit case. So that's what we'll look at next. So if you have a single qubit, that's represented by a 2-element complex vector. If you have a 2-qubit system, that's represented by a 4-element complex vector. But now, if you have a 3-qubit system, that's represented by, as you can see on the screen, an 8-element complex vector. So the size of the state vector representing the state is exponential in the number of qubits. And specifically, it is 2 to the n, where n is the number of qubits. This happens because the state vector of the joint system is the tensor product of the individual state vectors which represented each qubit, which grows exponentially. So we looked at how operations can act on a single qubit. There are also other more powerful operations which can act on multiple qubits. So for example, U2 in this diagrammatic representation is acting on 2 qubits jointly. This is an abstract example. When I go to the code, I'll show you a concrete example of a 2-qubit gate, which we can reason about. And with that, I think I will switch over to the code. Before I do that, does anyone have any questions? Okay, I'll switch over to the code. And if there are questions, they're probably better answered in code anyway. Cool. So lambeq is a library for quantum natural language processing, but as a part of this, it also comes with a feature-rich quantum computing backend. So this allows to create and manipulate quantum circuits and to also evaluate them efficiently. So I'm going to dive into the notebook. So to start, I'm importing lambeq's quantum backend, or rather, I'm importing everything from the lambeq quantum backend. Let's begin by creating the basis state that we saw at the beginning of the slides, where there is a class called get, which initializes a qubit and produces the sort of diagram we saw earlier, which is a qubit initialized in state 0. There is a small note on notation here where circuits are typically drawn from left to right. In lambeq, we always draw them from top to bottom. And the reason for this will become more clear when we get to the NLP portion of the talk. Right. So get 0 is so far unsurprising. If we evaluate this circuit that we've created by calling eval, lambeq gives us the linear algebraic representation of the diagram. Similarly, we could have initialized the state to be in state 1 instead. And if we evaluate it, we get the other basis states vector representation. And now that we've seen what the basis states look like, we can perform some logical negation on them. So the logical negation operation is called the X gate, which is just provided as an object in lambeq. So here we've prepared a qubit in state 0, negated it using the X gate, and we want to look at what the state of the qubit is after this. So we prepare this. We prepare get 0, compose it with logical negation X. We can draw it and evaluate it. And we see that we now get 0, 1, which is the state vector corresponding to get 1. And if I take get 1, I logically negate it and I evaluate it, I get 1, 0, which is the state vector corresponding to get 0. So here I'm confirming that state 0 negated's evaluation is the same as state 1's evaluation, which it is. So it's worth pointing out in this diagrammatic notation that states are boxes which take in no input and produce a wire. And gates on a single qubit are boxes which consume a wire and produce a wire. That is, they consume a state, act on the state, and produce the output of the state. This is a view that will help us when we try to connect some diagrammatic NLP techniques to quantum computing. Now we did the poly X gate. We can do rotation by some arbitrary angle 0.3. And if we evaluate this, now we see that the state vector we get as a result is not one of the basis states, because we didn't start with a pole and end at a pole. We started at a pole and ended up somewhere on the surface of the Bloch sphere that didn't coincide with one of the named states we've looked at so far. So this is a linear combination of two of the basis states. And in particular, you can see that it is a complex linear combination where the coefficient in the second term is complex. So that was the single qubit sort of section of this notebook. Does anyone have any questions on this?
This is available somewhere, right?
The notebook?
Yeah.
Yeah, I will figure out how to get this to the audience.
Okay.
Probably we will share it in the slide channel.
Okay, that sounds good. So yeah, and I will also share links to lambeq's documentation, which describes this in a lot more detail and describes sort of more powerful things that you could affect with the same generators. So now we can look at the 2-qubit state, where I've taken get 0, and this symbol here is how we do parallel composition in lambeq. So it's the @ symbol. So I've created 2 get zeros and I have parallelly composed them or tensored them together. Since the operation on the underlying linear algebra is a tensor product, we'll call it just tensoring the two states together. So that's what this looks like. So this is now a joint system with 2 qubits as its output. Now we can evaluate what the state vector for this looks like. And it's a 4-element vector. At this point, you could just out of curiosity see what the state vector would look like if you chose 0, 1 instead of 0, 0 as the two basis states. You'd get a different state vector here. And it would just be the tensor product of these two of the state vectors of these 2 qubits individually. Now, if I take 3 qubits instead of a single qubit, I can evaluate it once more and see that it's an 8-element vector. Nothing super surprising here. I can now act on this system as well. So here, what I'm doing is I'm tensoring together 3 get zeros, 3 states initialized in the 0 state, and I'm composing this sequentially, which is what the right shift operator does, with logical negation tensored with just the identity on 2 qubits. So another way to draw this would be the identity on the 2 remaining qubits, which looks like this. And now if we evaluate this, we see that we've gotten a different state. And in particular, you can check that this evaluates to the same thing as 1, 0, 0. Yeah, so that's true in all cases. So it's just the first qubit that's been flipped, and everything else remains the same. Yeah. So yes, I see a hand up.
So just quickly, how flatten works? How does flatten work?
Yeah, so flatten is just so evaluating something returns returns a NumPy array, which is shaped like the underlying tensor network. So if you have so all evaluation in lambeq happens on or the most efficient way of evaluating a circuit in lambeq is by representing the quantum circuit as a tensor network and then contracting that tensor network. And the number of sort of open legs or the dangling legs on that tensor network determines the shape of the output in general. But we know that since this is a state, we want to represent it as a state vector. So we just call like NumPy flatten on that.
But wouldn't, so in the above example, you have 3 qubits. Wouldn't the flatten give you 6 when it's flattened out?
Right. So this comes from the tensor product construction of the tensor product mechanism of combining 3 qubits or any n qubits. So the state vector, which represents n qubits, has length 2 to the n. So n in the exponent rather than in the product. So for 3 qubits, that's 2 to the 3 and 8 elements.
I see.
And this is sort of the first inkling of where the power of quantum computing comes from, because for a polynomial number of qubits, we are actually operating on an exponential size state vector under the hood.
Mm-hmm.
Right. Cool. So we've looked at a bunch of single qubit gates. We've looked at how we can put some single qubit gates together, and how we can put single qubits together, but we haven't really operated on the joint system yet. So there are some gates which you can, which act on pairs of qubits that can't be broken down into individual operations on the 2 qubits. And a simple example of this is called the C0 or CX gate. So its operation is very easily explained in English, where it flips the state of the second qubit if and only if the first qubit is in state 1. So if the first qubit is in state 0, it just returns the system as is. If the second qubit is in state 1, it returns the first qubit still unchanged, but flips the second qubit, which is what this truth table here demonstrates. So in lambeq, again, CX or control not is provided as a native gate. And it looks like this. So here the black dot is on the control, and this plus, the O plus is acting on the target. There's a control and the target in the system. So if you evaluate this, if you evaluate just this gate without applying it to a state, it's represented by a matrix which is 4 by 4. So it acts on 2 qubits and produces 2 qubits, which is why it's a matrix, while the states were vectors. So the operation of a gate on a state is a matrix vector product, where the gates matrix is multiplied with the state vector. Right. So we can look at the operation of the C0 gate on the system. So if we feed in the 0, 0 state, we should get as output, again, the 0, 0 state, which is what this state vector corresponds to. And again, a good way to check this is to just evaluate both. So yeah, and this is true. Now, if you take in get 1, 0, now we would expect the second qubit be flipped. And yeah, and the output that we get is for the 1, 1 state. So in this 2 qubit state vector, when we're dealing with basis states, the 4 elements of the state correspond to 0, 0, 0, 1, 1, 0, and 1, 1. You can view it as a one hot vector. So yeah, that works as expected. And if we do get 1, 1, if we evaluate get 1, 1, we see that indeed the vectors match. So far we've looked at fixed gates, but in addition to fixed gates, we really want parameterized gates, because eventually we're going to want to do some machine learning with these circuits. So a parameterized gate is one where the action is parameterized by a symbol or a variable of some sort. So in lambeq, there is a symbol class which allows you to create a variable. So in this case, I'm creating a variable theta. It looks slightly untidy here because I'm providing it in LaTeX representation so that it draws correctly later. So, and now I can create a rotation about the x-axis, which is parameterized by this symbol, by this variable that I've created, theta. So this is a parameterized gate, and if I draw it out, you see that it's an Rx by an angle theta. But when we want to compute with this, further you can see that it's a parameterized gate because it has something called a free symbol, which means that it has a parameter that needs to be substituted in before you can evaluate it meaningfully. You can evaluate it even in its variable form, but then the result that you get isn't a concrete tensor, or it isn't a concrete matrix. What you get is a symbolic tensor, where again you need to provide in a symbol to get out the concrete value. To get the concrete value, in lambeq we have a function called lambdify, which takes in so the parameterized gate provides the function lambdify, which takes in the symbol which we're going to provide to it at execution time to produce the concrete gate. So we create this lambda function. The lambda function will take in a symbol and will take in a concrete value for the symbol and will substitute it in and produce a concrete gate for us. The way that works is like this. So I've called the lambda function with the concrete value 0.2, and that's given us a Rx 0.2 gate as expected. So this will come in handy when we go to do some machine learning and NLP with this, because we'll represent our NLP model as a parameterized circuit. And the training procedure for a QNLP model is updating these parameters theta during training. So representing it in this sense lets us have a symbolic representation for our model, which can be instantiated at each training step with the parameters of that step. Right. So that's the end of this notebook. Does anyone have any questions at this point?
maybe if you could just quickly go up a few lines. I'm just wondering how that theta is applied. We know that it's, how does Rx apply theta? Is there a known formula on how that value is?
Yeah. And in fact, if we look at so when Rx of theta still just had a theta, and I evaluated it, you can look at this symbolic matrix. So this symbolic matrix is what exists in the code. So an Rx gate has a template matrix which will be applied for all theta, and that matrix contains some trigonometry on the angle that you provide, which you can actually conveniently see in this notation. So there's
theta is, so in essence, theta is how much is the degree of the angle you want to rotate your, yeah. Okay.
Yeah, exactly. It's the angle by which we want to rotate the state vector about the x-axis.
Got it. Thank
Which
you.
can dynamically change. Yeah. So currently we're operating in a fairly toy regime where we're looking at just individual gates or a couple of gates at most. In practice, there are like hundreds of thousands of gates in these circuits, but depending on the scale of the task and the scale of the data that you're operating on. Yeah, cool. Okay, and with that, I think I can go back to the presentation. So now we've talked about the quantum computing foundations for QNLP. Now let's take a brief look at NLP. I'll spend a little less time on this because I expect that this audience is much more familiar with NLP than with quantum. So yeah, so NLP at a high level is just using AI to model human language. By modeling language, I mean understanding language or gleaning information from language or generating language. So sentiment analysis is an example of understanding language where a model looks at text and gleans some information from this, such as, is this tweet positive or negative in sentiment? Machine translation and chatbots are on the generate language part of the scale, where not only does the model need to understand language, it also needs to be able to produce realistic samples. So that's the framework in which I'm going to think about NLP as I present QNLP models later. And something that's often taken for granted in classical NLP and has sort of become standard practice is that the input to a model that operates on text is a vector representation of the text on which it's operating. So typically, text is tokenized. Perhaps a simple way to tokenize text would just be into words, and each word or token is then assigned a vector. In classical models, this is typically a real vector, which you could get by using BERT or word2vec or fastText or equivalent representations. And the model then is something which takes in as input these vector representations of the input tokens and produces an output. This slide is meant primarily to show the diagrammatic framing of things that I assume are not super new to anyone in the audience. So yeah, the model takes in these vectors, and here, perhaps on the previous slide, note that already a sort of similarity is emerging between the diagrammatic representation that we use between the representation I use for quantum circuits and what we're going to use for language. So again, here I'm using triangles to be preparation of a state or preparation of a vector. And this parallel will serve us well as we continue. That's right. With the understanding that this is what a model is, we can now go to compositional NLP. So in general, the stuff that goes inside the model does not tend to look at the grammatical structure of text, at least in a lot of contemporary models. The components of the model are powerful linear algebraic components mixed in with some nonlinearities. Though it's also possible to fill in this model box with some structured components, which is what we'll look at now. So parse trees are one way to represent the grammatical structure of a sentence. So there are statistical parsers which can take as input text and produce as output part of speech tags for each word in the text and produce a parse tree for the text. So there's several variants of what this parse tree or parsing structure can look like. There's the pen tree bank style parse tree. There are universal dependencies. And the one that we'll use is combinatory categorical grammars, which I'll introduce in a slide or two. So if we begin with a sentence, a simple one, like Alice draws diagrams, a grammatical parse representation of this can look something like this. So on the left is the Pentry bank / universal dependencies style of representation, where each word is assigned a type. So I think it should be noun, transitive verb, noun. So this sort of parse tree, I assume, is more familiar than the ones on the right. So on the right are parse trees derived from the CCG framework, which has its roots in category theory, which I won't go into too much, but it's this grammatical structure on the right, which we're going to use for a couple of models that I show when we go to the code. So on the bottom right is a CCG parse for the tree, and on the top right is a more tree-like structure, more tree-like compositional diagrammatic structure derived from the same grammar, which already, if you sort of squint at it, you can see fits into the model box that we saw a couple of slides ago, where the words are represented as vectors at the top of the diagram. These are consumed by a model, which produces an output. And this is going to be the structure that our quantum models of language are going to take. Another example which is used in practice in QNLP is the DiscoCat model of language, which again uses the CCG grammatical parse of a sentence to produce diagrams which look like this, where the words are vectors at the top, and these are combined by these by this cup construction and identity wires on some types. And these annotations on the wires are parts of speech, so nouns and sentences, and there can be phrases and other types. This is probably the most abstract bit of the talk, but I'll switch over to the code now to show how these constructions exist in lambeq and how these can be used to come up with computational structure. Yes.
Can I just quickly ask you a question? If you go back to the previous slide,
Yes.
I guess the top part is similar to what NLP, like dense representations of, it's similar, but we're just replacing that typical binary vector representation with a quantum representation, right? The part that seems to be different is this compositional part, where you assume there's always a compositional relationship between the elements. So is the assumption there that we always know what sequence of compositionality needs to go in? So for instance, if you're doing a sentiment analysis here or a part of speech tag, you know that somehow that draws and diagrams need to go composition first, and then the result of that is a part of the second, and so on, or there's a process for learning that as well.
Right. It depends on the specific structure that you choose to have for your model. So in this particular structure where you're trying to come up with this tree which uses the CCG structure, you do require a CCG parse of the text. And there are statistical CCG parsers that exist. In lambeq, there is a Bobcat parser, which we develop and maintain, which does exactly this, which takes in a sentence, produces a statistical CCG parse for it, which can be converted into a diagram, which looks like this. There are other similar tree-like structures, which can be used, which don't rely on these grammatical assumptions as well. And I'll share a couple of these as I go to the code.
Thank you.
Yeah. Cool. So let me switch over to the code then. Cool. Okay, so now we're going to look at a sort of parallel submodule in lambeq, which deals with parsing sentences and producing abstract grammatical diagrams, which is closely related to the quantum representations which we saw earlier, but there is no quantum component to most of what I'm going to show here. This is I'll get to how this connects to the quantum bits halfway down. So let's begin with a sentence which we are going to parse, and all the models that I'm going to go through, I'm going to generate that model's diagram for this sentence. So if we don't have a grammatical parse, so we don't have grammatical structure, like the last question, we can still come up with a very simple compositional model, which just uses stairs. What I mean by stairs is something like this, where you simply take all the words in your sentence, starting from left to right, and compose them together with this very simple left-leaning binary tree. So in this structure, we didn't need a parse for the sentence, and we could just compose this linearly to form the structure. But again, we have the same words at the top, model in between, producing a single output with this grammar agnostic tree. So in lambeq, this is exposed through the stairs reader interface. So stairs reader is a reader which can convert sentences to diagrams. So it takes in a string representation like this, and produces a grammar diagram, which looks like this. So the type of this, in addition to providing a quantum backend, lambeq also provides a grammar backend, which represents diagrams in this style. These are abstract and don't natively come with any computational interpretation. And a large part of what lambeq does is mapping these structures onto a computational structure. Or giving these structures a computational interpretation, right? So the next level of model, after we've gone from trees with no grammatical structure, is to trees that do have grammatical structure. So here, lambeq provides a tree reader, which under the hood uses a CCG parser to produce a new tree, a grammar informed tree, which looks like this. So this is similar to what we saw on the slide, where the grammatical parts of the text was used to produce this tree structure. And there are different levels of granularity for this tree structure, such as it's possible to have a different box at each level. It's possible to assign these vowels the actual part of speech type for each word, but this is a relatively high level diagram, which still uses grammar. The next step in this is what lambeq originally started with, and a lot of original work in quantum NLP used this representation of text, which is called a pre-group diagram or a discocat diagram. So discocat is distributional compositional categorial, and it produces diagrams which look like this. So a key difference between this and the models we've seen so far are that the only boxes in this diagram are the words. There are no boxes like this unibox or the stair in the pre-group diagram. It's only the words followed by these cups and identities which connect the words. So if you buy for a second that the only trainable components are going to be within the boxes and not in the wires, then this represents a model where the only trainable components are the vector representations of words, which which is interesting because this can be mapped onto quantum computation in a very natural manner. In particular, a lot of initial work in QNLP was through the DiscoCat model by Bob Cooker and others. And they approached this from the mathematical field of category theory, pointing to relations between the structure of quantum computation and grammar in the CCG formalism. Though we don't need to go through all of the math because lambeq exposes this relation fairly neatly. So now, using lambeq's parser, we've produced this diagram, which has a box for each word and a bunch of wires. But now we really want to compute with this. And in particular, we'd like to compute with this on a quantum computer. So how do we convert this diagram into a quantum circuit or a quantum computation instruction? So we do this using something called an ansatz. So let's take a toy example where we have a single word. So this word is a state which produces a single wire. We need to map this to a quantum circuit, or to map this to a quantum circuit, we need to fill in this box with some sort of quantum circuit, and we need to choose how many wires this quantum circuit is going to, this state is going to have. So in lambeq, there are multiple ansatz provided. So an ansatz is precisely a circuit template which can be used to fill in these boxes. So here I've chosen one of the ansatz which come pre-packaged in lambeq called the IQP ansatz. To this, I specify that I want to assign the type null 4 qubits. And I say that I want a single layer of that circuit template to be filled into that box. So I create this ansatz, and now I can simply apply this ansatz to the box and produce a quantum circuit, which, if I draw out, looks like this. So I specified that the circuit should be on 4 qubits, which is what we see here. And the rest of the circuit represents a single layer of the IQP circuit. And it's worth noting that some of the gates in this are parameterized. So the RZs here, the controlled RZs, are word N0, word N1, and word N2, which, so word underscore type underscore index are parameters that can be trained during, that can be updated during training by some sort of gradient descent procedure. We can also look at it by querying the free symbols in the circuit, as we did for Rx theta earlier. Yes, are there questions?
So is it safe to say that this particular circuit had some desirable characteristics, and therefore this is embedded as a library in, like, as a function in your library?
Right. Yeah, so there are a few different reasons that that make for good circuit choices. Typically, you want circuits which are expressive. That is, changing the parameters in this can reasonably explore the space of all possible states on 4 qubits in this example. And also, if you're going to eventually run these algorithms on a real quantum device, you want the circuit to have properties that are compatible with that device. So, for example, different quantum devices have different native gate sets and have different quantum gates that they can implement. So you'd want an ansatz which uses those gates. In addition, you'd want to pick topology, which maps onto your quantum device well. Because in general, not every qubit, for most quantum devices, not every qubit can connect with every other qubit. So you'd want the topology to also be compatible. So there are multiple there are some machine learning reasons related to expressibility, which motivate choice of ansatz. And if the circuit is going to be run on an actual device, there are constraints of the device, which also motivate this. The IQP ansatz is fairly popular in sort of QML literature, which is why it's included in lambeq. There are some other ansatz which were largely chosen because they're very highly expressive.
Thank you.
Right. Yeah, so in this way, we started with a sentence. We created this grammar diagram for it. And then using an ansatz, we mapped the grammar diagram down to a quantum circuit. And now this quantum circuit is something that we can compute with, and most importantly, something we can train, which is what's going to be in the final part of my talk now. So are there any further questions at this stage?
So essentially, you're learning those rotations on each of the qubits the same way you're learning the values of each of your indices within your representations, which are like your vector representations. You could think of it that way, right?
Right. Yes. You're learning the state vector representation for each word, and that state vector representation for each word is parameterized by these rotations. So yeah, learning the angles for these rotations is a proxy for learning the state vector itself.
Makes sense.
Cool. Then I shall go back to slides. So yeah. Yeah, so we started with a diagram like this, and we can map it to a quantum circuit, which looks like this with free symbols. And now that we have this symbolic quantum circuit, which represents text from our data set, we want to begin learning with it. And the learning process is fairly standard. It looks a lot like a classical optimization routine, where you start with some parameterization for your gates. You compute the output of your circuit using this parameterization. You compare the output with an expected value in the case of supervised learning, measure a loss function, which you use to calculate gradients for your parameters, produce an update, and then proceed to your next parameters and repeat the process all over again until the model converges by some measure of convergence. Right. So this is what the sort of pipeline looks like in lambeq and in QNLP in general. You start with a sentence, you take its grammatical parse, produce a diagram, map it to a quantum circuit, and then go optimize it for a particular problem. So yeah, I think I can now switch to my final notebook, which is an end-to-end example using lambeq. Cool. So so far we've looked at relatively toy examples. Now we're going to be a little bit more ambitious and try a sort of task that works on real data. And so what I'm going to demonstrate here is the paraphrase identification task using lambeq. So there are two questions that we're going to answer. The first that the model is going to answer. The first is, given two phrases, do they have the same meaning? So yes or no, given a pair of phrases. And the second question, which we'll get to later in the notebook, is given one phrase and a corpus, can we pick an element of the corpus? Can we pick a phrase from the corpus which is closest in meaning to this query phrase? So for this, I'm using the PPDB paraphrase database dataset, which comes with a bunch of positive samples. So I'm using the phrasal version of it. You can download the dataset from this link. I'm using the phrasal small version to keep the sort of sentence sizes limited and tractable for this example. So here I'm just loading in the data set as one would. I'm removing some redundant pairs. I'm preparing a train test split. One problem with this data set that we need to solve for our task is that it only comes with positive samples. We also want negative samples to train the binary classifier. To do this, what I'm doing below is just randomly sampling pairs, which with high likelihood do not have the same meaning. Yeah, that's all I'm doing here. In this cell, I'm also preparing what the expected output of the model will be for various pairs. So here in this list comprehension, you can see for the true pairs, I expect the model to output 0, 1, that is that is the state vector that I expect the model to prepare. So I expect it to prepare get1 for instances where the two phrases have the same meaning, and I expect it to prepare 1, 0, which is get0 for a pair of phrases that don't have the same meaning. We can look at some examples of what the data set looks like. So presented to the assembly, be submitted to the General Assembly, have the same meaning, applying the principle of, implementation of the principle of, same meaning. So these are the positive samples. And the negative samples generated by negative sampling are sort of random. With high likelihood, the pairs aren't in any way correlated. Right. So now that we have these sentences and we have the pairs and the labels that we expect for them, we can begin the steps of the pipeline that I showed on the slide right now. The first part of which is creating the grammar-informed diagrams. So here I'm using the depCCG parser, which is included in lambeq, which is loading. My laptop is slightly burdened at the moment, so it might run slower than I would like it to. Yep. Yep. So now it's going through the phrases in the training and test sets and producing the diagrams for them using the sentences to diagram method. Yep, okay, that's done. So now I can draw a pair of the diagrams. So here's the first pair presented to the assembly, be submitted to the General Assembly in pre-group diagram form. And what we will get to at the end of the diagram, at the end of the notebook, is that the output of the quantum circuits corresponding to these two diagrams should be about the same. So after we prepare such a diagram, there are some rewriting steps which we can apply. Some of these are motivated by language. For example, you might want to remove stop words such as the to reduce the parameter space of the model and just get rid of extraneous information. So those are the sort of NLP motivated rewrites. There are also quantum computing motivated rewrites where, for example, we might want to use fewer qubits for the model, which means that we want to make the diagrams narrower in a sense. So I'm applying a whole host of these rewrites here. It's not super important which ones I'm applying, but there are a bunch of these available pre-made in lambeq, and there's also room to add your own custom rewrite, which operates on these diagrams. So yeah, here in this example, I've removed the word the from these two sentences, reducing the number of parameters in the diagram and also making it narrower. So now we have for each pair, we have two separate diagrams, but I want to represent these as a single diagram because I'm going to be computing on the pair together. Which is what I'm doing here. So the first sample now is this joint diagram, which has both of the sentences, just both of the phrases tensored together. Some standard shuffling. I'm setting up loss function and accuracy. lambeq provides its own set of loss functions, which are numerically stable and compatible with lambeq models and trainers, which we will see in a second. And now, we're given a diagram like this mapped to a quantum circuit. We want to compare these two wires and see if they carry the same state. So here's one method of doing this. This isn't canonical, and there are special cases in which you can do much simpler things. This is just one way of comparing the two states on each of these qubits and producing a single output, which is get1 in the case that they're the same, and get0 if in the case that they're different, and some value in the middle representing uncertainty in the output. Yeah, so at this step, I'm applying an ansatz. So here I've chosen a different ansatz, the SIM14 ansatz, which the reference is in the documentation of lambeq. This is a very expressive ansatz and provides a sort of rich parameterization for each word. I apply the ansatz to each diagram and I compose it with the equality comparator. So now evaluating one of these diagrams produces a single qubit or a state on a single qubit, and that state being in 1 or 0 is the output that the binary classifier, that's the output of the binary classifier. So this is what that joint diagram looks like. So at the bottom here, these bottom 4 or 5 gates are the comparator. This is one of the 2 phrases, and the stuff at the top is the circuit corresponding to the other phrase. It's not super important to look at this diagram and look at the specifics of each of the gate, but broadly, it's the circuit corresponding to 2 phrases stuck together, plugged into the equality comparator. So now we've finished processing our data set. We have the quantum circuits that we're going to optimize. Now we need to set up a model and a trainer. So in lambeq, there is a quantum trainer and a NumPy model. These are just one choice each from a host of models and trainers that lambeq provides. Which I can describe what the others are later. But for this example, we're using the NumPy model, which evaluates the circuit by representing it as a tensor network and then contracting that tensor network. Use JIT_true tells the model that we want to use Jack's acceleration for the linear algebra operations. Yeah, so I create the NumPy model from all the circuits, and I create a quantum trainer. So this quantum trainer is given the model, it's given the loss function, number of epochs, optimizer that we're going to use, and some evaluation metadata. So the optimizer here is worth looking at for a second. In general, in cases where you have access to autodiff, you could use Adam, where you have access to exact gradient information for all of your parameters and you can do autodiff, you could use Adam. SPSA is an optimizer which does not assume knowledge of the gradients. It uses multiple samples. It uses multiple samples of the forward pass to arrive at an approximation of the gradient, which is what it uses for optimization. And these are some standard hyperparameters for SPSA. Now we create a lambeq dataset, which just batches and shuffles the data appropriately to be consumed by the trainer. And now we have a trainer, we have a dataset, and now we're ready to go. So now we can just call trainer.fit on the training dataset and the val dataset, which will sort of run the training loop for as many epochs as we specified. So this can take a little bit of time to run. So I've prepared another version of this notebook where I've run the notebook past the training. So that's what the training loop looks like. And we produce at the end some stats on the training and validation data set. So we can see that the model definitely learned to converge on the training data set, though its generalizing performance was somewhat limited, which is to be expected because I used a very small subset of the data set that was available and the vocabulary is largely unbounded. Or is much larger than the number of samples we had. So we would expect the model to not be able to generalize given the small amount of data it's seen. So now that we've trained the model in this setting.
Excuse me, how much is the size of the training data here?
I think I limited it to 100 samples. So the original data set, I think, has several thousand samples. I just truncated it down so that I could efficiently create the circuits and diagrams to show here live. So yeah, now we have trained, we've trained this binary classification model, which can take in a quantum circuit representing 2 phrases and compare the 2 quantum circuits to tell if they're the same or not. Effect, and use this to determine if the original 2 phrases had the same meaning or not. Now that we have this, we can apply it in practice to the second setting, where we have a query phrase and a corpus of multiple phrases, and we want to find the closest phrase in the corpus in meaning to the query phrase. So here, I just picked the first example as my query text, which was presented to the assembly, which we saw in the diagram earlier. And I create a corpus where I just take some small subset of the other diagrams from the second elements of the pair. And now I can compose the query circuit with each element of the corpus and compose it with the equality comparator as shown here. So this is effectively creating a diagram for the query with each element of the corpus. Are they the same in? Oh, that's very for for the query and for each element of the corpus, do they have the same meaning? Yes or no? Which the output for which we can get by calling the model on each of these diagrams that we've prepared. So this yields for each word, for each corpus, for each element of the corpus, what is the probability that it has the same meaning as the original sentence? And now we can simply take an argmax on the second column to determine which of these quantum states is closest to the 0, 1 state, which we can do this way. And I can get in this, I've also gotten the phrase which corresponds to that highest probability. And we can see that it makes sense. It is, in fact, close in meaning to the query phrase. So, right, this was an example of how you can use each component of the lambeq stack to start with text, produce diagrams, derive quantum circuits from those diagrams, and train them on sort of real world data. So yeah, does anyone have any questions at this point? So this was the end of the demo. Okay, so maybe I'll switch back to the slides for a second. So yeah, I think that was the majority of my presentation. That's all the practical stuff that I wanted to talk about and all the code that I wanted to go through. QNLP is a sort of much broader field than the stuff that I've shown here today. And there's some links for further reading and to get hands-on with some of the stuff I've shown here. So lambeq is an open source Python package. It's available on PyPy, so you can pip install lambeq. It's open source, so it's available on GitHub. If you have any questions, further questions about lambeq, or you have trouble getting something set up, you can reach out to us either on GitHub or on our Discord, on the QNLP Discord, where me and the other lambeq developers are active and sort of will help you out. And yeah, if you want to do some further reading on QNLP or lambeq in specific, here are some references. And I think I will I'll find a way to share these slides with you. Cool. So, that's the end of my talk. I'm happy to take questions.
This was really good, Nikhil. Very informative. I have a question, but maybe I'll ask my question when we start recording.
Sure.
So I'll stop recording now.